talking about set theory, and we're going to start on arithmetic proofs. I will give you a test back at the end of the class. So last time we talked about set theory, we did an introduction to that, and so I put everything we did last time on one slide. Okay, so we talked about different operators for sets and Venn diagrams for them. So we talked about union, where you take all the points from two sets and put them together into a new set. We talked about intersection, where you take points that are in both sets. So union was like what operator in logic? Or, intersection was like and minus is all the elements of A that are not in B. By the way, this is logically equivalent to A minus A intersect B. So you can actually see the picture is the same as if I would have had this minus this little football. Because the things that are in B but not in A never could have been in A minus B to begin with. Okay, A exclusive or B is like the inverse of this picture. All the stuff that's in A or in B but not in both. We have subset, so if a set is entirely contained inside another set, so all the elements of A are actually in B, then A is a subset of B. We talked about cardinality. If you have a set that has 4 things in it, we say the cardinality is 4, and the way we denote that is with like the absolute value sign for sets. So the reason why that we use that sign is because what does that sign actually mean mathematically? Or in physics? Magnitude. So that's actually why we use it for the size of a set, because its magnitude is what is the size of the set. Okay, we talked about a universe of discourse, so that's the universe where we're selecting items for our set. And we talked about complement, which is like not in logic. So the complement of a set is everything in the universe that is not in that set. We talked about an empty set, which is the set with no elements in it. There's only one of them. The size of that set is 0. We also talked about De Morgan's for sets, which is if I take the complement of a union, we get the intersection of the complements, which is exactly the same as we got in our logic. And it works because the definitions of these sets are basically from logic. They're from ands and ors, so when we use nots, we get the same kind of stuff. So are there any questions on any of these topics? Like I said, this is your relax after we had a test material. I am not, by the way, going to go over the test in class. You may ask any questions you want about your grading. The best way to, if you don't like how something's graded, is to ask a question, is to post it as a private post on Piazza to your instructor group, because then any one of us, 6 of us, can answer your question. If you just email me, it will take me longer than if it's on Piazza and one of the TAs can answer it. The other thing is you can also come to one of our office hours and we can check over it. Okay, so there are no questions on these basic definitions. Okay, good. So the next thing we need to talk about so you can do your homework is power sets. So a power set is the set of all subsets of a set. And that could be a tongue twister. So a power set is written like this. So this is our new kind of notation we learned last time. We write a curly brace, then we write the type of element it is. So this is like a variable that represents one single element. This vertical bar means so that. And then to the right of that just tells us what kinds of things can be in the set. So it's sort of like a little set of directions for creating the set. So the way I read this is the power set of S is the set containing A, items A, so that A is a subset of S. That's how we read it in English. And you're probably still looking at it going, that actually doesn't tell me very much. Okay, so let's do an example. For example, we have the set A. It has two elements, 0 and 1. That 0 is not an empty set, it's just a 0. We use this set all the time for our logic variables, right? That's where they come from. They come from the set 0, 1, the values of them. Now the power set of this is the set of all subsets. So it is, first I draw a curly brace for the set, and then the empty set is the smallest subset of any set. The empty set is contained in every set. So the way that I think about figuring out the power set is I take the original set, and then I think about taking out all the stuff. And there's an empty set right there, if I take out all the stuff. And then if I put one of the items back in, that's my first element. If I put the other item back in, that's my second element. And then leaving them all there, that's my last one. And that's for a size 2 power set, making the power set. It's going to be the same no matter what the elements are. So there are always, for any set that has 2 elements, there are always 4 elements in the power set. Okay, let's do another example. So let's say B is the empty set, and it contains no elements, so the size of B is 0. The power set of that is the set containing the empty set. Since there are no other subsets of the empty set, that's it. So we're done. That is the power set. Notice, though, that the size of the power set of B is 1, because it does contain an element. That element happens to be the empty set, but remember that a bag with nothing in it is not nothing. So you should think of sets as containers, and they are actually things. Yes? The power set of B is not a subset of B. So you just asked me, how can the set containing the empty set be a subset of the original set? It's not. So this is a subset of this. So all the elements of P of B are actually subsets, but the set itself actually is much larger. And it's a set of sets. B might not actually have sets in it. So the power set always is a set of sets, whereas the original set might not be. So thank you for asking the question. That's very clarifying for people. Other questions? Okay, so like I said, the way I think about it is I cross out no elements all the way up to all the elements at a time to make all the different subsets. So you're probably thinking, wow, this is too easy. Why are we even doing this? Because, like I said last time, we like to be able to understand what are all the possible inputs for a program. How many things am I anticipating? How many different cases can I have for different kinds of problems? And what are all the possible values for things that I might get? So we have to do these kinds of things for programs and for being computer scientists. Okay, so let's do an example of a power set. So I'd like you to figure out, so this is going to be S. I'd like you to figure out the power set of S and also how many elements are in that power set. So write that down on your paper and then check it with your neighbor. That we have. The empty set is always the smallest one. Okay, what are the one element subsets? The set containing A, the set containing B, the set containing C, and then we have all the 2 element subsets, AB, AC, BC, and then we have all the 3 element subsets, and there's only one of those. So that's the whole power set of S. Every single power set that of a set where the original set has 3 elements looks exactly like this. So when you get a problem that looks extra tricky, you're allowed to relabel the things, figure it out, and then plug back in. Let me give you an example. Here's another S. A lot of people mess up with examples like this. It is not hard. The easiest thing to do is to do this. And then S is now equal to what? AB. Super easy to do the power set. Let's do it. Empty set, set containing A, set containing B, set containing A and B, and I'm done, right? Always the same. It's not a different process no matter what the elements are. And then I can plug back in. Whatever A is, I just copy it. Whatever B is, I just copy it. So you can use this process whenever you want to figure out a power set and that's got confusing elements in the original set. Just don't use those. I'm pointing this out because this is where people make the most errors when they're trying to figure out power sets, is that they get tripped up with a whole bunch of curly braces. Well, you can just get rid of them and do the problem and then put them back in. Any questions? Yes? This answer in WebAssign would look like this. Okay, it's not just WebAssign, it's sets in general. Okay, this is not, it wouldn't be any less painful if you had to do something else. You have to write all these curly braces. You have to match them up. Yes? You must write curly braces. Please don't use square brackets. The reason why you don't use curly braces on WebAssign is because they are a special character and they get turned into something else by the automatic grader. So you don't want that. So you have to use the braces. So curly braces is how you should write them on a test. Okay, yes, it's a pain in the butt. Does anybody know a workaround that will help you make sure you match the right number of brackets before you type it into WebAssign? Spaces is one suggestion. Yes, that is nice. If you put spaces, it's easier for your brain to match them up. Do it what? Copying an empty set and pasting it wherever you need it is fine, but don't do the empty set symbol because WebAssign doesn't know how to read that in the answer thing. Yeah, but the pair of brackets, yes, that is good. Yes? Yes, if you're writing it on paper, do the brackets bigger and smaller so you can tell which ones match. Use different colors. Yes? Right, so you could always add an ending brace whenever you add a new one. So therefore you'd never have the wrong number. Okay? Yes? Right, so you can do it in a text editor and do find and replace when you're done. So you can find and replace for empty sets. I was thinking put it in Excel with actually regular parentheses and it'll check them for you and match them and color them. So there's a whole bunch of stuff you can do. Like also if you just opened an IDE and you start putting some braces in, it'll match them for you. So you don't have to do it all, like typing in the little teeny boxes. Do it somewhere else and cut it, paste it in there. So you have tools and brains. So use them so you don't make mistakes. Okay, many, many options for doing this. But basically, empty sets are a pain, and just work without them as much as you can and then put them back in. Okay, so the next thing we need to do, actually I want to tell you a little bit more about sets. So one of the ways that we actually can denote sets, or the power set of something, is a cool mapping that gets used a lot when we need to talk about sets. So, you know, we're computer scientists, so we really love binary. And the reason why we love it is because it's so useful. So we've already decided collectively that braces are terrible, right? And yet we need them. Why do we need them? For sets, yes. But why? Why am I using braces to denote sets? It encapsulates them, right? It's like these are the things I'm talking about right here. And we do it in programs. Why do we do it in programs? No. Why do we put braces in programs? For the same reason. For scope. That's a different word than encapsulate. For scope, right? So I need to tell where something starts and where something ends. And right? And I might have some stuff inside that has start and ends, and I need to know where they are. That's what we use braces for. Okay? But we hate them because it's hard to make sure they match up. Right? So that's a source of human error. So a lot of times we need to come up with another representation that we won't make so many mistakes on. So binary is a great example. So here, for example, if I want to talk about, let's say the power set of S, and this set right here, I can actually make a binary vector, and the first place in my binary vector is going to be whether A is in this set, the second one's going to be whether B is in the set, and the third one is going to be whether or not C is in the set. So the set ABC can now be represented with a 3-digit binary number. Right? So A is in S, right? B is in S, and C is in S. So each one of these is a 0 or a 1, telling me whether or not A is in the set, B is in the set, or C is in the set. Is anybody in here a game programmer? Anybody? Couple? Okay. Does this look like anything in a game program? Any other kind of program? Okay, combinatorics. I was thinking about flags or triggers. So we use flags for lots of stuff, right? To tell if somebody's going to come into a room or not, to keep track of whether somebody has put in their credit card information, whatever I'm doing in a program. I often need flags to tell me whether something has happened or not. So, and they're usually binary valued. It's either yes or no. So, and we almost always keep them in some kind of vector because it's very efficient for space. Okay, so what is the representation for S given this 1, 1, 1? So S can be written in this new notation as 1, 1, 1. How do I write the empty set in this notation? Well, that's right, the empty set is 0, 0, 0. Now the power set is what? All the combinations of binary numbers, and there's 3 of them. And that is why there are 8 members in the power set, because it's all the possible 3-digit binary numbers. Let's list them. That's the empty set, the set containing C, the set containing B, B and C, A and C, A and B, A, B, C. No braces. I didn't hear any cheering. Gee. Okay, there you go. Thank you. You're probably like, so? This is very cool because now if I need to store like a set in something, I don't have to like match up a bunch of braces and put a whole bunch of commas, right? And now you're going to be like, why don't you rewrite WebAssign so we can put that in? Maybe I'll do that. So post that on Piazza if you want me to. But I'm not doing it by tonight. Not by tomorrow. I have to teach another class tomorrow. Maybe. You want to come over and help? Okay, so when we talk about sets and power sets of sets, it's because we actually use sets and power sets for denoting like all the possible things I might get as an input. So let's say, for example, that I give you a bike lock and you've got 3 roly things on it and it just has 2 numbers on it. This is also all the possible combinations I could have for the bike lock, right? Do you want a bike lock that only has 8 possible combinations? No? It's easy to remember, right? Because even if you forget, you can get it pretty fast, but so can everyone else. Because they could try all the 8 possible combinations. So if I have more digits on each possible position, right, we have more combinations, we multiply all the numbers by each other to get how many we get. So how many do most locks have on them, combination locks? Like maybe 4 by 10, 4 digits, 10 of them. So if I have 10 choices in each, that's 100 times 100. How much is that? 10,000. Okay, so that's 10,000. You don't really mind if someone has to stand there by your bike to try 10,000 things, right? First of all, they're probably going to forget and redo a bunch of them, so they even have to do more than 10,000. And then you'll probably be back there before they finish. So that's why we have combinations. It's not because it's actually going to keep somebody from, guessing what our thing is. And that's why passwords, it really matters, like how long they are and how many possible things you use in your passwords. Because if someone can write a program to try all the combinations, it really doesn't take that long to do 10,000, right? But people don't usually do that, like in front of your bike, because even in front of your bike, they'd have to turn the thing, so that takes time. So we're lucky that computers can't turn locks. Okay, so this is a good way of listing all the possible things I might see. Now, sometimes if I need to go through all the possible kinds of subsets I might look at in a program, I might actually use a register in the computer to count, like all of my possible subsets, like all of these. Okay, does anybody know what a register is? Raise your hand if you know what a register is. Raise your hand if you don't know what a register is. Okay. So a register is what? So some of you raise your hand. Somebody give me a definition. It's a temporary storage. It's not just temporary storage. It has a particular purpose, right? Usually registers are for stuff that I want to do things to. So either I want to read it and print it out, or I want to add something to it, or subtract something to it, or fetch something from a memory location. So your registers are basically like your working memory space for your computer, the very small, very fast working memory space for your computer. Okay? And they have a position for every bit they can read in. And when you say you have like a 64-bit processor, that's like the size of your registers. It's also the size of the bus that will send data back and forth between things. So that's how many bits you've got in your registers. And those are like when we did our adders before. So our arithmetic logic unit connects like 2 registers together and can add them. And it has the circuit for adding 2 registers together. All right, and it'll have a result register. So it'll have 2 input registers and an output register. So that's the kind of stuff that we've got. So in a register, though, if I have to go through the numbers from 0 to 8, let's write them down again. I have to flip bits to do that, right? So when I go from 0 to 1, how many bits do I have to flip? 1 bit. To go from 1 to 2, how many bits did I have to flip? And to go to 3, how many? How many? How many? That's kind of a pain that it's uneven, right? Wouldn't it be nice if I could just flip 1? Why do I care how many bits I have to flip? What'd you say? Yeah, time delay slightly. Yes? What else? What did you say? But why do I care? Why do I care about how many bit flips it is? It takes time to flip the bits, right? And energy, right? So I'd rather, if I'm trying to actually get the most out of my processor, which we don't do anymore because memory's so cheap, but if I want to, I actually only want to flip one bit at a time. Right? Also, something has to calculate what these different numbers are. I don't have like a huge table of looking up what the next number is. So I actually have to add 1 to the number to figure out what the next number is. That's kind of a pain. So I actually have to do extra calculations every time I want to go through a list of things. It's not such a great idea. So it would be really cool if we could flip by 1 bit every time. Can anybody do that? I'm going to give you a couple minutes. See if you can rearrange these numbers so that they flip by 1 bit every time. And you can work with your neighbor to do it if you want to come up with a strategy together. Let me hear some of your algorithms for flipping the bits. Let's write them down. Yes? Okay, you got all the numbers. That's good. How did you come up with that? Okay. That's great, but it doesn't scale to the next problem, right? Anybody else come up with an actual algorithm? Did you raise your hand in the back? You're double checking yours? Oh, put 0, 1, 1? Put 0, 1, 1 after that, 0, 0, 1? Should I cross out the zeros? Do you have an algorithm that gave you that? Okay. Okay, how about yours? So what's your algorithm? Okay, so that's an algorithm, so let's write it down. So the first step was to start at 0, 0, 0, right? So then we flip the leftmost bit, or no, the rightmost bit. Which one did you go to? 0, 0, 1? Okay, so let's flip the rightmost bit. And then we flip the next one, right? Well, then we go to this one, right? So then we go to the next one. So we keep doing that again. So then we get 1, 1, 1. And then do we wrap around or do we start going back to the right? What did you say? Okay, so go back to the right. So when you hit the left side, start going left, start going right. Is that correct? Okay, so that means that I'm going to flip this one next, right? And we're still going right. So we go right till we hit the right side, right? So then we're going to go 1, 0, 0. We do hit the right side, so then we're going to go back the other way, right? Let's just do the next one. So go right till we hit the right side. We did hit that one, so we flipped this one. So then we're going to flip that one, right? So we're going left now. So we flipped that one, and then we need to flip this one. So we went left. Now we need to go right again. And that's all of them, right? So that was good. This is kind of a pain, right? It tells me how to do it, but there's another way to do it. And it is called a gray code. So it's really easy to solve the problem of how do I go through an entire list of numbers, flipping only one bit at once for a really short list. Right? Yeah? Like if the list is length 1, you're done with the whole list on the first number, right? This is easy. Done. Right? Okay, solving that problem is easy. Now, I solved the 1-bit problem super easy. The 2-bit problem is also, well, that's not all of the 1-bit problem, right? The 1-bit problem also has a 1. Yes? So, we got 1-bit, super easy, and then if I wrap around, I'm still at a 1-bit flip, right? So that's good, because then I can rotate as many times through if I need to. Now, if I want to do this for the next number of bits, think about our truth tables. In our truth tables, part of the table looks the same, like repeated, but the leftmost bit is 0 for the first half and 1 for the second half. If we do that, let's say we put zeros in front of these and copy this again, but we take the mirror image. So take the mirror image of our original list, just flip it across, and then put zeros in front of the first half and 1s in front of the second half. That gives us a sequence that's 1-bit flips every time, and it will go back around because I put a 0 in front of this one, and I put a 1 in front of that one. So there's exactly 1-bit difference because they're flipped. And I can do it again, right? So I can just copy this entire thing. Like mirror across. So what I'm doing is copying across like this. And I can put zeros in front of these. And 1s in front of those. Isn't that cool? And you can do that forever. And you're guaranteed that the last one is going to match the first one. So I think you're bouncing back and forth. It would be harder to prove that it would always be correct. Yes. I'm not sure if it's called a canonical ordering, but it is a gray code. Okay, so this is called a gray code. And it's a way to go through an entire list of numbers by flipping 1 bit at a time. And we'll talk about recursion later, but we just did this recursively because we solved a really, like in order to solve a large problem, we solved smaller problems. We broke it down into 2 smaller problems. So in order to do for 3 bits, we did the 2-bit problem, copied it over twice, put zeros in front of the first half, 1s in front of the second half. That is a recursive solution. Okay, so another way to look at power sets, and I'll relate this back to the gray code in a second, is we sometimes draw pictures of power sets where we actually draw like the empty set first. And let's say we want to do the power set of ABC. So sometimes we list ABC at the top, we list the empty set at the bottom, and then one level above the empty set, we list all of the one-element subsets. And then one level above that, I list all the 2-element subsets. And then what I do is I connect with the line sets in adjacent levels that are subsets. So the lower level, if it's a subset of the one in the higher level. So the empty set is a subset of all the ones on the next level, right? So I'm going to connect them all up. And then A is a subset of what on the next level? The first two, right? And then B is a subset of AB, and the set containing B is a subset of the sets containing AB and BC. And C is in these two. And then all three of these are in this one. What'd you say? Okay, so somebody saw one thing I wanted you to see. It looks like a 3D cube. Yes? Now, another cool thing is if you actually put the gray code representation, so if you put the 3-digit representation on each of these, any path over this cube is a gray code. Because I've only joined adjacent subsets if they differ only in one position, right? So A is a subset of AB and AC, so these are joined to two things that have one more element, right? So actually this is 0, 0, 0, right? That's 0, 0, 1. That's 1, 0, 0, and 0, 1, 0. This one is 1, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. So any path through here also is a gray code. So any path that starts and ends at the same place is a gray code. So we'll do some more with this kind of notation later, but I wanted to show it to you now when you're doing power sets because power sets make these cool pictures. So no matter what size the power set is, it will make a picture like this. So if it's got more elements, it will just be fatter, but it'll look very similar. So gray codes have good applications for making sure that we list all the numbers in between two numbers, list all the subsets of a possible set, and do it with minimal time and energy and loading into registers and that sort of thing. So it's pretty cool. They're also used for some other stuff, but I don't have time to talk about it today. So the next thing we need to do, though, is to talk about cross products, and you guys have seen these all the time in other places. We just want to formally define a cross product. So here's how we write it. An X is the cross operator. And so this is a set A, that's a set B. So we write it in set notation as the set containing little a, comma, little b, so points where little a is in the set A and little b is in the set B. And that's kind of an and. So if you see commas in these, it really means and. Okay, so I'm going to give you a couple of sets, and I want you to figure out what's the cross product. Okay, so try that out, and then we'll come back together. So try it out, check with your neighbor. Okay, so if you don't know what to do, we turn on Robot Brain. Robot Brain says copy down stuff. Okay, so I have a curly brace. I have to put some points in here. That's like one of the elements has to look like that. The first thing here has to come from A, so let me put 1 in there. The thing here has to come from B, so let's put C there. Okay, that's one of the elements. It looks like this. So yay, I did that correctly. Let's try it again. Let's put a 1 in the first part. Can we put something else in for the second part? What can we put in? We can put D there. Good, we did 2. So now I don't think there's any other combinations between A and B where I have 1 as the first thing. So let's put 2 and C, and then 2 and B. And then we're done. So it's easier than you thought if you were sitting there wondering what to do. So this thing, when we do this notation, whoa, that was weird. When we do this notation, it is a pattern matching notation. Okay? So that means that everything in AB has to look like this, and I have to do all the things that look like that. So how about B cross A? Is it the same set? No, because the first element has to come from set B. So it is going to be very similar though, right? Just take all the elements and flip them. So flip the position for all the points. Okay, you guys have been dealing with cross products forever on the XY coordinate plane. The XY coordinate plane is one representation of a cross product of what with what? What are the two sets that points on the XY coordinate plane are coming from? The real numbers. So the Cartesian coordinate plane is the reals crossed with the reals. So every single point on a Cartesian coordinate plane is in a cross product of the reals with the reals. And when we draw a point, that's exactly what we're doing. We're doing exactly this. We're taking one point from the reals, putting a comma, putting another point, and putting parentheses around them and saying this is a point in this space, where the first one's from the x-axis and the second one's from the y-axis. Any questions so far? So your homework asks you to do all the different kinds of things we've been talking about today. With some basic sets just to make sure you know the definitions and how to apply them. And there was one more thing I wanted to do today. There it is. Okay, so one of the things you have to do is actually write down what the Cartesian product for something is. You also have to figure out a couple of intersections and unions of sets, also something pretty easy. The hardest thing you're going to have to do is something like this. We're going to be given a predicate. And then we have some different quantifiers. And we need to figure out how often they're true for a given function. So P of xy is going to be x and not y, or not x and y. And then when I ask you for all x for all y, is P of xy true? Without knowing what P of xy is, what should your guess be? No. Why? It should be no, because I'm basically asking you, is the function P of xy always true no matter what? So for all x for all y, P of xy means P is true no matter what, right? And most functions aren't like that because they're mostly useless. Right? That's like having a password, and no matter what people type, just let them in. Okay? We don't do that. So most of the time, we don't actually have functions like that. So if you're going to guess on something, guess at 0 for this. But how do we actually figure it out? Draw a truth table for P. That's what we should do. We know how to do that. It's easy. Okay, then we figure out x and not y. So x is false in those two. I'm sorry, I just totally did that opposite of what I was supposed to do. There we go. All right, and then not x and y. And then I OR them together. So now I can check, if I check for all x, for all y, p of x, y, I'm actually looking at this final column because that is the final output of this function. And I'm checking to see is it all ones. Well, that's not, so let's put 0 for that. For there exists x, there exists y, p of x, y. What is that asking me? Is there any case where this is true? Yes? It's almost always going to be true, right? Because also the function that's all zeros is also mostly useless. That's like having a password and no matter what somebody types saying no. We make games sometimes with jokes like that, right? Like, find the key for this door. There is no key. All right. How about for all x, there exists a y, p of x, y. What is that asking me? That's right. For every value of x, there's some value of y that makes p of x, y true. So what I need to do is try for x equals 0, can I find a y that makes it true? And for x equals 1, can I find a y that makes it true? So the easy way to do this in a truth table is just to split the table for the x values. And in the top part of the table, make sure there's a 1. There is. Right? And in the bottom part, make sure there's a 1. There is. So for x equals 0, I can use y equals 1, and for x equals 1, I can use y equals 0, and now I have shown that for every value of x, there is a value of y that makes this true, so this is true. P of x, y is exclusive OR. How about this? There exists a y for all x, p of x, y. What is that actually asking me? So pick a y value, and then no matter what x is, p of x, y has to be true. Is that the case? How do we know that there is no such y value? There's only 2 y values. I can try them both and then see if the x, if it doesn't matter what x is. So I can try y equals 0, right? And so then I can actually plug that into the function. So I can say x and 1, or not x and 0. This is always going to be 0, right? So x and 1, is that always going to be true? No, it's not. So y equals 0 doesn't work. Let's try y equals 1. So I can try x and 0, or not x and 1. So that's going to be 0. So this is going to be the result. Is that always true? No. So no matter what, I can't actually find a y value that will give me a true for p of x, y no matter what. So this is false. And I want to be able to do the same thing with the x and y's reversed. So now, do you think we can find an x value that makes the function true no matter what y is? No, because it's exclusive OR, right? So if I set x, y is supposed to be the opposite. So no, this is going to be false. But what about for all y, there exists an x, p of x, y? I heard a yes. Why is that? the same thing with the truth table. We can look for y equals 0. Are one of those two rows true? Yes. When y equals 1, are one of those two true? Yes. So every time, every value of y can find a value of x that makes it true. And since it's exclusive OR, x has to be the opposite of y to make it true, right? So we actually know a formula. So for every y, as long as I put in the x that's the opposite, then I'm going to make it true. So now we know that this is true. So the reason why we're doing these kind of problems is because we want to be able to tell, like, how often is a function true? Or is one of the values actually independent of the other values? If it is, if I can pull it out front, it's independent. Okay? So that's one of the kind of tables you need to do for your homework. Any questions on that? Okay, so that was the basics for set theory. That's some of what we do for this. Let me try one more thing that we need to do. So we talked about cardinality. There's a couple of other things we need to do. So the inclusion-exclusion principle is something we want to do. Okay, the inclusion-exclusion principle is for us to actually understand the cardinality of a set whenever it's a combination of other sets. So, for example, if I want to figure out how many elements are in A union B, I'd like to use the number of elements in A and the number of elements in B to figure that out. And my first guess would be to add them. Is that your first guess? Well, I certainly shouldn't subtract them. And I definitely shouldn't multiply them, right? We only multiply when for everything in one set we do something with an element in the other one. We're not doing that. We're just adding them all together, so it makes sense to add them. But is that correct? Why not? There's some overlap, probably some overlap between the sets. So if we have A here and B here, there's some stuff in here that gets counted twice, right? So how do I get rid of those? I can subtract the intersection because those are the only things that got counted twice, right? The things that are in both A and B, if I take them out once, then they only get counted once. That is the inclusion-exclusion principle. So if I have two sets and I take their union, I can figure out how many elements are in there by adding up the number of elements in my two sets and taking out the intersection. Okay, we want to prove that we can use this for a union of 3 sets. So I want you to use this to figure out a formula for A union B union C. What does it mean to use this for that? This is a formula that you can use. So what is A union B union C actually? Can we take the union of 3 things at once? No, we don't. We do pairs, right? So in actuality, there's some parentheses in there. Where should we put them? Around A union B, maybe. Okay? Then what do? Once we have done that, now this is a union of how many sets? 2. And this is a union of 2 sets, right? And it doesn't matter what the letters are, so I can actually use that rule for the 2 sets right here. So for this set and that set. So this says take the first set and add the size of the second set and then subtract the intersection of my 2 sets. The cool thing is I already have a formula for this, right? So I can just copy that for that part. The size of A plus the size of B minus the size of the intersection. Copy this over. So this was these terms right here. And this one looks a little wonky. It's an intersection, and we don't have a formula for the size of an intersection, right? But we can use the distribution rule that we had in logic so that the main operator on here is a union instead of an intersection. So the way we do that is we take this and C and we put it with each of these. So we take A and C and then take the union. With B and C. So I copy this and stick it on each of these elements and put the union in the middle. So that's called the distribution law, and it's the same for sets as it was for logic. Now once we did that, that's a union of how many sets? 2. So now we can use our formula again with these 2 sets. So I'm going to call this X, and then I'm going to figure out what X is. So X is equal to A intersects C plus the size of B intersects C minus the size of the intersection of these 2 things. Okay, so I need to plug X back into my original equation, but before I do it, is there anything we know about this last thing to make it look a little simpler? A intersects C intersected with B intersects C. We've got 2 intersect C's in there, so we only need 1. That's like ands. Remember, it's like ands. And remember that C anded with C. I can rearrange these any way I want because it's all the same operator. They're all ands. So we can rearrange them, and then we'll get A intersect B intersect C. So this one can be rewritten as A intersect B intersect C. There's no more unions left in anything, so we can't use our formula yet anymore. So let's actually plug this in for X. So we have the size of A plus the size of B. And while we plug in, I'm going to rearrange. I'm going to do all the single element ones first. Yes. And then we're going to copy over the minus A intersect B. And then copy over. So we have a minus X here, so these have to be minuses. Minus A intersects C. Minus B intersects C. And then we have a minus for the X and a minus inside the X, so that makes a plus. So we do plus A intersects B intersects C. So once we have done this, can you make a guess of what the formula for this is? So it looks like we add the individual sets, right? We subtract the intersections of 2 sets. Then we add the intersections of 3 sets. And then we subtract the intersections of 4. Make sense? And that does work. So that will be the size of A plus the size of B plus the size of C plus the size of D minus all the intersections add called the triple intersections. How do we know when we're done with all of the intersections of 3 elements? How do we know how many there should be? Each one's not going to have, like, it'll be leaving out 1 every time, right? So there should be 4. So am I done? Which one am I missing? Okay, and then I need to subtract what? The intersection of all of them. So we can alternate the signs between all the different sides. How does this relate to the power set of a set? Well, this is like, basically this is a list that's like all the subsets, right? If I think of A, B, C, D as a set of sets and then all the subsets of it, this is all the different subsets, right? Just pairing them together, not looking at the operator in between them. So we have some similar, kind of stuff to do with looking at all of the combinations in here. So we're actually using all the combinations of all the letters there. So these are related to each other. So let me show you a picture of the triple one that might help make this more concrete. So here's the triple. Here's A, B, and C. And we draw it this way in case there's some overlap in some of these different little pieces. So if I start to figure out how many elements are in here, it's all the elements in A plus all the elements in B plus all the elements in C. Okay, so the stuff that's just an A and nothing else never got counted more than once. So we don't have to worry about that. That's why we're subtracting stuff in intersections, because the things that weren't in intersections never got counted more than once. And then in here, this part right here, so we actually take this, what is this football? That's A intersect B. So that's why we had to take it out. So that's just like when we did A union B, we had to take out the football because it got added twice. Well, right here it got added twice, and right here it got added 3 times. So we take this out once, but the ones in here are still in there twice. We're not going to worry about that yet. So then we also take out B intersects C and A intersects C, right? So everything here is okay. Everything in this half football is all right. And this half football is all right because we've taken out one copy of it, and everything in that half football is all right. But this stuff in the middle got taken out how many times? It got taken out 3 times, so I need to add it back in. So that's actually where this, like you can see a picture of it. Every single point, you can consider the different points. Where is it on the diagram? And count how many times it got counted in this expression, and you'll find out that each element only gets counted once when we do it right. So there's another little trick that we use with sets to actually do proofs about them. Okay, so you can actually prove this one other way. So we actually proved this kind of recursively using a formula more than once, but we can also do it with a truth table. So the truth table is going to be a set of propositions. So I'm going to start to use shorthand for intersect. So I'm just going to leave a times in there because I don't have enough room to put x's in on this whole thing. So literally each one of these is going to be x's in, A intersect B intersect C. So if A, B, C, A, B, A, C, B, C, and A union B, union C. So we fill this out like we normally do. Okay, and then we just find out if x is in, like these are actually true and false values, so I just check and see if x is not in any of these, can it be in the intersection of ABC? No. Is it in AB? It's not in any of this stuff. It's not in anything. Okay? If it's just in C, it's not in any of the intersections, right? But it is in the union. If it's just in B, same thing. Okay? And if it's in B and C, it's going to be in that one. If it's in just in A, it'll be in that one. Okay, and if it's in A and C, it'll be in that one. And if it's in A and B, it'll be there. And if it's in all three, it'll be in those. I messed that up. It is in there. Sorry about that. Okay, now if you look at this, look across the rows, each of the rows, if I add up all the values, it actually adds up to what's in the right-hand side, right? Well, if we look at those, not necessarily these. So what we need to do is look across here, and we actually said that A union B union C actually has the same number of elements as plus on these, right? Minus on these, and plus on this. So let's actually see if that works. So 0 plus 0 plus 0 plus 0, subtract all of these. Does that equal 0? Yeah. Okay, how about 1, subtract these? Gives me 1. 1, subtract these gives me 1. 2, subtract this gives me 1. 1, subtract nothing gives me 1. 2, subtract 1 gives me 1. 2, subtract 1 gives me 1. And 4, subtract 3 gives me 1. So that's actually a proof of our inclusion-exclusion principle using a truth table. Because all the points that are in the union have to be described by one of these possible rows. So that's all the possibilities for X actually being in A union B union C. And that's how you can count them. See you next time.